For most of human history, the universe appeared as a collection of separate mysteries. The motion of the stars followed patterns that seemed disconnected from the fall of an apple. Electricity crackled with a personality of its own, magnetism pulled iron as if by magic, and the forces inside atoms were completely unknown. Physics advanced by isolating these phenomena, studying them one by one, and building theories that worked within limited boundaries. This approach was powerful, but it also created a fragmented picture of reality. The idea of unifying physics arises from the realization that these fragments may not be truly separate at all, but different expressions of a single, deeper order. At its heart, unifying physics means connecting all fundamental forces into one coherent framework. Today, physicists recognize four fundamental interactions that govern everything we observe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each has its own mathematical description, its own domain of influence, and its own history of discovery. Gravity shapes planets, stars, and galaxies. Electromagnetism governs light, chemistry, and technology. The strong force binds atomic nuclei together, while the weak force enables radioactive decay and fuels the reactions inside stars. They appear distinct, yet the dream of unification suggests that this distinction may be superficial. This dream is not new. In fact, it has driven some of the greatest breakthroughs in science. When Isaac Newton described gravity with a single law that applied equally to falling objects on Earth and to the motion of the moon, he performed an early act of unification. He showed that celestial and terrestrial mechanics were not separate realms, but part of the same physical story. Centuries later, James Clerk Maxwell unified electricity and magnetism, revealing that they were inseparable aspects of a single electromagnetic force. Light itself emerged as an electromagnetic wave, and what once seemed like unrelated phenomena became manifestations of one underlying interaction. These successes inspired physicists to search for deeper unifications. In the 20th century, the weak nuclear force and electromagnetism were shown to merge into a single electroweak force at high energies. This discovery was not merely theoretical. It predicted new particles that were later confirmed in experiments. It demonstrated that forces we perceive as distinct under everyday conditions can become unified under extreme circumstances. This insight strengthened the belief that the remaining forces might also fit into a single framework. Yet gravity stubbornly resists this unification. While the other forces are described by quantum field theories that excel at explaining the behavior of particles at microscopic scales, gravity is described by general relativity, a theory that treats space and time as smooth, continuous structures. These two frameworks are both extraordinarily successful, but they are fundamentally incompatible in their current forms. Attempts to apply quantum rules to gravity lead to mathematical inconsistencies, while treating gravity classically fails at the smallest scales. The unification of physics, therefore, demands not just a combination of existing theories, but a profound rethinking of their foundations. To unify all fundamental forces would mean finding a single set of principles from which gravity, electromagnetism, and the nuclear forces naturally emerge. In such a framework, forces might no longer be seen as separate entities, but as different ways in which a deeper structure interacts with itself. Just as temperature emerges from the collective motion of molecules, forces might emerge from more fundamental ingredients that reveal themselves only at extreme energies or tiny distances. One powerful idea suggests that symmetry lies at the core of unification. Symmetry, in physics, refers to transformations that leave the laws of nature unchanged. Over time, physicists have discovered that each fundamental force corresponds to a particular symmetry. The more symmetric a theory, the more unified it tends to be. By identifying a grand symmetry that encompasses all known interactions, physicists hope to show that the diversity of forces is simply the result of that symmetry being broken as the universe cooled after its birth. In the earliest moments after the universe began, conditions were unimaginably hot and dense. Under such extreme circumstances, the distinctions between forces may not have existed. All interactions could have been unified into one. As the universe expanded and cooled, this unity may have fractured, much like ice crystals forming different patterns as water freezes. The forces we observe today would then be remnants of an original unity, shaped by the history of cosmic evolution. If this picture is correct, unifying physics is not about inventing something new, but about uncovering something ancient. It is an attempt to reconstruct the original simplicity of the universe from the complexity we now observe. In doing so, physicists seek answers to questions that reach beyond equations. Why does the universe have the particular set of forces it does? Why do they have the strengths and properties we measure? A unified framework promises not only consistency, but explanation. The implications of such unification extend far beyond abstract theory. When forces are unified, they impose constraints on what is possible in nature. These constraints can explain why certain particles exist and others do not, why some processes occur while others are forbidden, and why the universe has remained stable for billions of years. Without the precise balance between forces, atoms would not form, stars would not shine, and life, as we know it, would be impossible. Unification thus connects the smallest scales of physics to the largest questions about existence. At a deeper level, unifying physics reshapes our understanding of causality and interaction. In current theories, forces act through the exchange of particles, such as photons for electromagnetism or gluons for the strong force. In a unified theory, these exchange particles might themselves be manifestations of a single underlying entity. What we interpret as different messengers of interaction could turn out to be variations of the same fundamental excitation, shaped by context and energy. There is also a conceptual elegance to unification that appeals to the human mind. Simplicity has long been a guiding principle in science, not because nature must be simple, but because simple principles often generate complex outcomes. A unified theory would embody this idea at the deepest level, showing how the rich tapestry of physical phenomena emerges from a small set of fundamental rules. This elegance is not merely aesthetic. It is a sign that a theory may be tapping into something real and profound. However, the path to unification is filled with challenges. Experimental access to the energies where forces unify is far beyond current technology. This means that much of the work relies on indirect evidence, mathematical consistency, and theoretical insight. Critics argue that without direct experimental confirmation, unification risks becoming speculative. Supporters counter that history shows theory often runs ahead of experiment, guiding it toward discoveries that would otherwise remain invisible. Unifying physics also requires humility. Each past unification has revealed that our intuitive categories were incomplete or misleading. Before Maxwell, electricity and magnetism felt fundamentally different. Before Einstein, space and time seemed absolute and separate. A final unification may force us to abandon deeply held intuitions about reality itself. Concepts such as space, time, force, and particle may be approximations rather than fundamental truths. In this sense, the unification of forces is also a unification of perspective. It invites us to see the universe not as a collection of independent parts, but as an interconnected whole. Every interaction becomes part of a single narrative, governed by principles that apply everywhere and always. This view dissolves the boundary between the cosmic and the microscopic, showing that the same rules shape galaxies and atoms alike. Ultimately, explaining the unification of physics as the connection of all fundamental forces is about more than solving a technical puzzle. It is about completing a story that began when humans first looked at the sky and wondered whether there was order behind its motion. It is about trusting that beneath the apparent complexity of the world lies a deeper coherence waiting to be understood. Whether or not the final theory is within reach, the pursuit itself has already transformed physics, revealing unexpected connections and pushing the limits of human knowledge. In following this path, physicists are not just chasing equations. They are seeking a vision of reality that is whole rather than fragmented. To unify physics is to affirm that nature, at its deepest level, speaks with one voice, even if that voice expresses itself through many forms. When physicists speak about unifying physics, they are not only talking about equations or forces, but about a transformation in how reality itself is understood. The second keynote points directly to this shift. Such unification would change how we understand space, time, matter, and reality itself. These concepts feel solid and familiar because they shape everyday experience. Yet history shows that each major advance in physics has quietly undermined what once seemed obvious. A true unification would not simply refine our picture of the universe. It would redraw it from the ground up. For centuries, space and time were treated as a fixed backdrop. Events happened within them, but they were not influenced by those events. This view worked well until the early 20th century, when relativity revealed that space and time are not separate entities, but aspects of a single fabric. They bend, stretch, and respond to matter and energy. Even this radical idea may only be an approximation. A unified theory would likely reveal that space and time are not fundamental at all, but emergent, arising from deeper processes that do not resemble geometry in any familiar sense. In current physics, space is something you can assign coordinates to, and time flows forward in a consistent direction. Yet quantum theory introduces uncertainty and discreteness at the smallest scales, suggesting that the smoothness of space and time may be an illusion. When gravity and quantum mechanics are finally unified, the concept of a continuous spacetime may dissolve. Space could turn out to be granular, woven from tiny units of information, or defined by relationships rather than distances. Time might not flow universally, but emerge from change itself with no independent existence. Matter, too, would be reinterpreted. What we call particles are already known not to be tiny solid objects, but excitations of underlying fields. In a unified framework, even these fields may lose their fundamental status. Matter and forces could be revealed as different modes of the same underlying entity, much like different vibrations of a single string produce different musical notes. The distinction between what is a particle and what is a force carrier may no longer make sense at the deepest level. This redefinition of matter would affect how we think about substance and identity. If everything is ultimately made from the same underlying structure, then the diversity of the physical world is not due to different ingredients, but to different patterns of organization. Atoms, stars, and living beings would all be expressions of a single physical language, written in different dialects. This idea challenges the intuitive notion that complexity requires fundamentally different building blocks. The unification of physics would also transform our understanding of reality itself. In everyday life, reality feels local and immediate. Objects exist in specific places, and causes produce effects in predictable ways. Quantum physics already complicates this picture by allowing non-local correlations, where particles influence each other across vast distances without any obvious signal passing between them. A unified theory might show that such phenomena are not anomalies, but natural consequences of a deeper structure that does not respect classical notions of separation. In such a framework, the universe may be better described as a network of relationships rather than a collection of objects. What matters most would not be where things are, but how they are connected. Space and time would then be emergent measures of these connections, useful approximations that arise when the underlying network is viewed at large scales. This relational view of reality would represent a profound shift from the object-centered perspective that dominates everyday thinking. Unification would also alter how we think about the beginning of the universe. Current cosmological models trace the universe back to an initial state where densities and energies become infinite, signaling the breakdown of known laws. A unified theory could remove this singularity, replacing it with a more complete description in which the beginning is not a point of infinite breakdown, but a transition governed by deeper rules. This would change the narrative of cosmic origin from one of failure to one of continuity. Similarly, black holes, which currently represent regions where our theories collapse, would be reinterpreted. Instead of being places where information is destroyed and physics ends, they might become laboratories where the unified nature of reality is most clearly expressed. Space and time behave in extreme ways near black holes, hinting that their familiar forms are not fundamental. A unified framework could reveal that what we perceive as paradoxes are simply artifacts of using incomplete theories beyond their limits. The everyday experience of causality might also be revised. In classical physics, causes precede effects in a clear temporal order. Quantum theory already blurs this distinction, allowing processes where cause and effect cannot be cleanly separated. A unified theory may go further, suggesting that causality itself is an emergent concept, meaningful only within certain scales and conditions. At the deepest level, reality might be governed by constraints and correlations rather than linear chains of cause and effect. Such ideas are unsettling because they challenge deeply rooted intuitions. Yet history suggests that reality does not owe us comfort. Each time physics has progressed, it has forced us to accept that the universe is stranger than common sense would predict. The Earth is not the center of the cosmos. Time does not flow at the same rate for everyone. Particles do not have definite properties until measured. Unification would likely extend this pattern, revealing that even space, time, and matter are provisional concepts. Despite this, unification would bring a new clarity. By showing how familiar concepts emerge from deeper principles, it would explain why our everyday intuitions work as well as they do, even if they are not fundamentally correct. Chairs feel solid because of electromagnetic interactions. Time feels continuous because the underlying processes that generate it operate far below our sensory resolution. A unified theory would not deny experience. It would place it within a broader context. There is also a human dimension to this transformation. Our sense of place in the universe is shaped by how we understand reality. If space and time are emergent, then our existence is not confined to a rigid cosmic stage, but part of a dynamic, evolving structure. This perspective can foster a sense of connection rather than isolation, as the same underlying principles that shape distant galaxies also give rise to our own bodies and thoughts. Unifying physics would therefore blur the boundary between the observer and the observed. In a universe where everything arises from the same fundamental structure, the act of observation becomes just another physical process, governed by the same laws as everything else. This challenges the idea that humans stand apart from nature as detached spectators. Instead, we become participants within the very system we seek to understand. The transformation of space, time, matter, and reality brought about by unification would not be a single moment of revelation, but a gradual shift in perspective. As with relativity and quantum mechanics, the new ideas would take time to be absorbed, debated, and refined. Textbooks would change, language would adapt, and metaphors would evolve. What once seemed radical would slowly become normal. In the end, unifying physics would remind us that our most basic concepts are tools rather than truths. They are maps, not the territory itself. By revealing a deeper level beneath space, time, and matter, unification would not strip the universe of meaning. Instead, it would enrich it, showing that reality is more subtle, more interconnected, and more profound than we ever imagined. When physics is finally unified, its consequences would not remain confined to chalkboards and research papers. The third keynote points toward a broader horizon. A unified theory would reshape technology, philosophy, and humanity's future questions. History shows that when our understanding of nature deepens at a fundamental level, the effects radiate outward into society in ways no one can fully predict. Unification would represent not just a scientific milestone, but a civilizational turning point. Every major leap in physics has quietly rewritten the technological landscape. The principles of classical mechanics made engineering reliable and scalable. The unification of electricity and magnetism laid the groundwork for power grids, telecommunications, and the digital world. Quantum mechanics, once dismissed as abstract and impractical, became the foundation of modern electronics, medical imaging, and computing. These advances did not arise because scientists set out to invent specific devices, but because deeper understanding unlocked new ways of manipulating nature. A unified theory would extend this pattern to an unprecedented depth. By revealing how all forces emerge from a single framework, unification could open doors to forms of control over matter and energy that are currently unimaginable. Technologies might exploit regimes where forces blend into one another, allowing transitions between forms of energy with extreme efficiency. Materials could be engineered at a level where their properties are not merely discovered, but designed from first principles. Energy generation might move beyond combustion and nuclear reactions toward mechanisms that draw directly on the structure of spacetime itself, guided by a deeper grasp of gravity and quantum effects. Computation could also be transformed. Today's computers rely on quantum effects only indirectly. A unified understanding of physics might enable entirely new paradigms of computation, grounded in the fundamental fabric of reality rather than in electronic components. Information processing could be intertwined with spacetime geometry, blurring the distinction between computation and physical evolution. Such developments would not simply make existing technologies faster or smaller. They would redefine what technology means. Yet technological power always raises ethical and philosophical questions. A deeper understanding of the universe forces humanity to confront its responsibilities. When energy becomes easier to manipulate and matter more malleable, the potential for both creation and destruction increases. Unification would therefore amplify the importance of wisdom alongside knowledge. The challenge would not only be what we can do, but what we should do. Philosophically, unifying physics would challenge long-standing ideas about causation, determinism, and free will. If all phenomena arise from a single underlying structure, then the apparent complexity of the world becomes a matter of pattern rather than principle. This could support a view of the universe as deeply ordered, even if unpredictable in practice. The tension between determinism and randomness, already sharpened by quantum mechanics, might be reframed as a feature of how deeper laws manifest at different scales. The concept of explanation itself would evolve. In everyday thinking, explaining something often means reducing it to familiar causes. A unified theory might require explanations that are abstract, mathematical, and counterintuitive, yet fundamentally complete. This would test the limits of human understanding, forcing philosophy to grapple with the question of whether explanation requires intuition or whether coherence and predictive power are enough. Unification would also influence how humanity thinks about meaning. Science does not assign purpose to the universe, but it shapes the stories we tell about ourselves. A fragmented picture of reality encourages a fragmented sense of place. A unified picture suggests coherence and connection. Knowing that the same principles govern the birth of galaxies and the chemistry of life can inspire a sense of belonging within the cosmos, even in the absence of cosmic intent. The future questions humanity asks would also change. Many current research problems exist because our theories are incomplete. Once a unified framework is established, attention would shift from patching gaps to exploring consequences. What kinds of universes are possible within the unified laws? Are there multiple consistent solutions, each corresponding to a different cosmic history? Could entirely different forms of matter or structure exist, governed by the same underlying principles but arranged in unfamiliar ways? Cosmology would enter a new phase. Instead of merely describing how the universe evolved, scientists could ask why it took this particular path. The relationship between the laws of physics and the initial conditions of the universe would come into sharper focus. Questions about whether the universe is unique or one of many possible realizations would no longer be philosophical speculation alone, but subjects of scientific inquiry grounded in a unified theory. Humanity's future in space could also be influenced. A deeper understanding of gravity and spacetime could make long-distance travel more feasible, not by violating known laws, but by exploiting them more fully. Concepts that currently belong to science fiction might be recast as engineering challenges rather than impossibilities. Even if such possibilities remain far in the future, the shift in perspective alone would expand the horizon of what humanity considers achievable. Education and culture would change as well. A unified framework would simplify the conceptual foundations of physics, even if the mathematics remains complex. Students would learn a single coherent story of nature rather than a collection of partially connected theories. This coherence could influence how other fields approach complexity, encouraging interdisciplinary thinking grounded in unifying principles rather than isolated facts. There would also be a cultural impact in how society views scientists and knowledge itself. The achievement of unification would stand as a testament to human curiosity and persistence, reinforcing the idea that reason and evidence can reveal deep truths about the universe. At the same time, it would highlight the provisional nature of knowledge, since even the most unified theory would remain open to refinement and reinterpretation. Importantly, unification would not eliminate mystery. It would change the kind of mystery we face. Instead of asking how forces fit together, we might ask why the unified laws are what they are, or whether alternative laws could exist. Instead of wondering how the universe began, we might explore whether beginnings are necessary at all within the deeper framework. Each answered question would give rise to new ones, often more subtle and profound than those that came before. The relationship between science and philosophy would deepen. Philosophy would not be replaced by a unified theory. It would be challenged and enriched by it. Concepts such as existence, reality, and knowledge would need to be re-examined in light of a world where space, time, and matter are emergent. Philosophy, in turn, would help interpret what unification means for human understanding and values. In the long view of history, unifying physics would be seen as a moment when humanity achieved a new level of self-awareness. By uncovering the deepest structure of the universe, we would also learn something about the power and limits of the human mind. The theories we build are products of our cognition, shaped by evolution and culture, yet capable of reaching far beyond everyday experience. Unification would stand as evidence that the universe is, at least in part, comprehensible. Ultimately, reshaping technology, philosophy, and future questions is not about providing final answers. It is about transforming the landscape of inquiry itself. A unified theory would act like a new lens through which everything else is viewed. The world would look different, not because it changed, but because we finally learned how to see it as a whole. The long pursuit of unifying physics is often described as a technical challenge, but at its core, it is a human story. The fourth keynote points inward rather than outward. The journey toward unification reveals as much about human curiosity as it does about the universe. Long before equations, laboratories, or instruments existed, humans looked at the sky and wondered whether there was an order behind its motion. That impulse, to search for unity beneath apparent diversity, is one of the defining traits of our species. From the earliest natural philosophers to modern physicists, the drive to unify has been motivated by a belief that nature is not arbitrary. This belief is not proven in advance. It is a working assumption, a kind of intellectual faith that the universe is coherent enough to be understood. Each successful unification has reinforced this assumption, while each failure has tested it. The process reveals a delicate balance between confidence and humility, a willingness to believe in hidden order while accepting that current understanding may be incomplete or wrong. The history of physics shows that unification is rarely straightforward. It involves false starts, abandoned ideas, and long periods of confusion. Many theories that once seemed promising were later discarded, yet these failures were not wasted efforts. They refined intuition, sharpened mathematical tools, and clarified what questions were worth asking. The journey itself became a source of insight, teaching physicists not only about nature, but about the limits of human reasoning. Curiosity plays a central role in this journey. Unlike practical problem solving, the search for unification is driven by questions that have no immediate application. Why are there forces at all? Why do they have the structure they do? Such questions persist even when there is no guarantee of answers. This kind of curiosity is patient and resilient. capable of sustaining effort across generations. Physicists often work knowing that they may never see the final result, contributing instead to a collective endeavor that extends beyond individual lifetimes. This long-term perspective shapes the culture of science. Knowledge is not owned, it is inherited and passed on. Each generation builds on the insights of the previous one, sometimes confirming them, sometimes overturning them. In the quest for unification, this continuity is especially clear. Ideas introduced decades ago may only find their proper place much later, when new techniques or perspectives make their significance apparent. The journey is cumulative, even when progress appears slow. The pursuit of unification also reveals how deeply human imagination is entwined with abstraction. The theories that aim to unify physics often involve concepts that cannot be directly visualized. Higher dimensional spaces, abstract symmetries, and mathematical structures replace familiar images. This challenges the mind to operate beyond intuition, relying on consistency and logic rather than sensory experience. In doing so, it expands the range of what humans consider thinkable. At the same time, imagination remains essential. Unification does not emerge from calculation alone. It requires the ability to see connections where none are obvious, to propose bold ideas that initially seem implausible. This creative aspect of science is sometimes overlooked, yet it is crucial. Theories that eventually succeed often begin as speculative leaps, guided by aesthetic judgments about simplicity and elegance. The willingness to trust such judgments reflects a deep engagement with the unknown. The journey toward unification also exposes the social nature of knowledge. Physics is not practiced in isolation. Ideas are debated, criticized, and refined through collaboration and disagreement. The search for a unified theory has generated entire communities of researchers, each bringing different approaches and intuitions. This diversity of perspectives is not a weakness but a strength, increasing the chance that hidden connections will be noticed. Human curiosity, however, is not purely rational. It is shaped by hopes, fears, and cultural context. The desire for unification reflects a longing for coherence in a world that often appears chaotic. Finding unity in the laws of nature can be emotionally satisfying, offering a sense of order and meaning. Yet this emotional dimension can also mislead, encouraging attachment to ideas that feel beautiful even when evidence is lacking. The journey toward unification, therefore, demands constant self-critique, a readiness to let go of cherished ideas when they fail. The tension between ambition and restraint is a recurring theme. Unification represents the highest aspiration of physics, yet it must be pursued with respect for empirical reality. Theories cannot be judged by elegance alone. They must ultimately confront observation. This tension mirrors a broader human challenge, balancing the desire to reach beyond current limits with the discipline to remain grounded in evidence. As the search continues, it reshapes how physicists think about success and failure. In many fields, success is measured by immediate results. In the quest for unification, progress is often indirect. A new mathematical tool, a deeper understanding of an existing theory, or a clearer statement of what does not work can all count as meaningful advances. This redefinition of progress reflects a mature understanding of inquiry, one that values depth over speed. The journey toward unification also invites reflection on the purpose of science itself. Is science merely a tool for prediction and control, or is it also a way of understanding? The unification program leans strongly toward the latter. It seeks not just to calculate outcomes, but to comprehend why the universe has the structure it does. This emphasis on understanding aligns science with philosophy, blurring the boundary between empirical investigation and deeper reflection. In this sense, unifying physics is as much an inward journey as an outward one. It challenges humans to confront the limits of their concepts, the assumptions embedded in language, and the frameworks inherited from history. Each attempt to unify reveals hidden biases in how problems are framed. By exposing these biases, the journey refines not only theories of nature, but also the tools of thought used to construct them. The pursuit of unification also highlights the humility required to face the unknown. Despite centuries of progress, the most fundamental questions remain open. This is not a failure, but a reminder of the vastness of what remains to be understood. Human curiosity thrives not on final answers, but on the promise of deeper insight. The willingness to continue asking questions in the absence of certainty is one of the most admirable features of scientific inquiry. Ultimately, the journey toward unifying physics reflects a broader human narrative. Across cultures and eras, people have sought patterns, connections, and underlying principles. This drive appears in myths, philosophy, art, and science alike. Physics gives it a particularly rigorous form, but the impulse itself is universal. In seeking unity in the laws of nature, humans are expressing a fundamental aspect of their identity. Whether or not a final unified theory is achieved, the journey will have lasting value. It will have expanded the boundaries of knowledge, refined the methods of inquiry, and deepened humanity's sense of wonder. The search for unification is therefore not only about discovering how the universe works, but about understanding what it means to be a species capable of asking such questions at all.